Hey, good morning, and welcome to the next lesson here in geometry. And what we're going to be talking about today is going to be our transformations. And as this is an introduction to transformations. We haven't discussed it yet in class or in limited. We haven't studied it yet. So what we're going to do is we're going to have an introduction to all the different types of transformations, and then we will follow that up with individual lessons on each transformation. So with this, it says, how can you determine if a figure has been transformed, and if so, the type of transformation? Well, all of our transformations are going to have certain characteristics. But more importantly, I guess, before we get started with that, let's talk about the things that will help identify transformation, and that would be corresponding sides and angles. And as we see here, corresponding sides are a pair of sides that have the same relative position in two congruent figures. So corresponding sides, if we look over here at our image, we have this trapezoid EFGH, and it says that it is congruent to trapezoid QRSP. Now, so there's many ways to look at the congruency or the corresponding parts. Remember, when we are naming something, the name has the order has purpose. When we name it, the order has purpose. So when I'm just looking at this name, EFGH, that corresponds to QRSP. So I could say that the segment EF corresponds to the segment QR just by looking at the order of the name. And if I come over here and I look, EF, right here is segment EF. It has one little congruency marker. And come over here, and then QR also has one little congruency marker. And if you look at it, you can sort of see that the shape. Maybe if we were to cut and look at this, we could turn around and say, hey, look, it's a little bit more evident that that's the same image. So as we look at these kind of things, and that's why they're saying that you can draw this conclusion. So I can see here, if I look at RS, right, corresponds to FG. Come over here and I can say that sure enough, RS has 1, 2, 3 congruency markers, and FG has 1, 2, 3 congruency markers. So I can look at the name of it and say, and be able to make these determinations, or I can look at the image and make those determinations. For example, HG corresponds to SP because there's my congruency markers match up. I could say that angle E corresponds to angle Q. Now, not only is it the same shape, but it is in between this, EF and EH, and Q is between RQ and QP. So I can see that angle E is between the 1 and the 2 congruency markers. Angle Q is between the 1 and the 2 congruency markers. So we're able to identify all of those things looking at it. And an example here would be angle S has 2 congruency markers, so its measurement is the same as angle G. And in order, I see that RSP, I have RSP corresponds to GH or FGH, FGH. So all of those sides correspond based on that order that the name is written. So there you go. Corresponding sides are a pair of sides that have the same relative position in two congruent figures. And then corresponding angles are a pair of angles that have that same relative position in two congruent figures. So as we start to now talk about these transformations, a transformation is a one-to-one mapping. Okay, one-to-one mapping of all points from one figure to another. So the mapping consists of, let's see, I'm going to go ahead and label some stuff here that I omitted. So if I QRS is mapped to TUV. So all points mapped. So let's see here. So in this figure, we would want to be able to recognize that S maps to V, R maps to U, and then Q maps to T, because every point in the pre-image maps exactly to one point in the image. So we would call this my pre-image. That's my starting point, my pre-image, and then my image is going to be my new location. And we'll talk about how sometimes when we do transformations later on is indicating the transformation, because we're going to use some different notations too in the future. So if I look here, example 1, considering this figure, I have W, X, Y, Z, complete the statements. Well, looking at this, I would have to say that W corresponds to C. And then, let's see, what else? X corresponds to D. So it looks like W, X, Y, Z corresponds to or maps to C, D, and if you notice Y, 3 congruencies, A, 3 congruencies, C, D, A, B. Okay, and if we look, we can see that B has 2 congruencies in between 1 and 2 segment, the 1 segment and the 2 segment, and then Z has 2 congruencies in between the 1 segment and 2 segments. So there we go. This would be a mapping to show W maps with C, X maps with D, Y maps to A, and Z maps to B. So the corresponding point W corresponds with, point W should correspond with point C. Angle ZWX. ZWX should correspond with angle BCD. BCD should correspond ZWX. And let's look. This, of course, is my vertex, C and W. C has 1 congruency marker, and then W has 1 congruency marker. So sure enough, they do correspond. So that should be angle BCD. And then segment XY. Segment XY corresponds to, well, segment XY corresponds to DA, and let's look. We have XY has 1, 2, 3, 4 congruency markers, and then DA, 1, 2, 3, 4 markers. So yeah, sure enough, that is going to be DA. So we can look at the image right here and do it, or we can look at, once we create the order of the name, we can also just use that information. So looking here at the different types of transformations now, we have rigid transformations. And what rigid transformations is an isometric transformation, or is an isometry, and it's a transformation that preserves the size, the lengths, the shape, the lines, the angle measures of the figure. Everything is preserved rigid. You know, it stays the same. For example, if I move a calculator from one desk to another, that calculator is rigid and does not change shape. Okay, it has just moved its location. It has transformed its location, but the calculator is still the calculator and still the same shape. Now the pre-image and the image are congruent. Again, everything is the same and equal, so they're congruent. As we look at this example, this first example right here, we have a reflection. And a reflection or a flip, all points of the pre-image are reflected across a line of reflection to become the image. So I'm not sure here, if I just say I have line M, it looks like this image has been a mirror image or reflection over that line. So this point corresponds to this point. This point corresponds to this point, and then this point corresponds to that point. So it has flipped like a coin. Now, when we look at this next image over here, this is a translation. And it is often referred to as a slide. And because it looks like this image has just been moved and slid over here, because all my sides and angles are still in the same relative position. So all the points of the pre-image will move the same distance and direction to produce the same image. Okay, so everything slid the same amount in the same direction. And actually all these would be parallel when they do the transformation, or that slide, or translation, should I say. I'm sorry. Now, here, this next one, we are looking at a rotation. And a rotation or a turn, all the points of the pre-image are rotated around a center of rotation. And that right there would be my center of rotation. And what we have is this point is equidistant from this point, so those are the same, okay? So my image has rotated right? I believe that's the case, and then this image rotates to here, and then this rotates to here. So as we go around the circle, all those are the... No, I did that wrong. Let me see here. This point right here, right here, right here. So as we rotate around that center of rotation, all the points would have traveled at the same measurement. And if we look here, we can see that here are my two congruencies. So this would stay, it would reference right here to the two congruency markers. And then we have what would appear to be a isometric triangle, because we have two legs that are same, and there are the two legs right there. So just being able to see the rotation, we're going to go into some practice on this, but just being able to see how it moves around. So in this example, one thing to consider, that when I look at a translation, everything traveled at the same direction and the orientation stayed the same. You know, this angle corresponds to this angle. With a reflection, everything seemed to be reflected over a line, and then this point would be equidistant from the line that this point, because it's a mirror image. So this little segment from the line to the point would be the same as this segment from the line to the point. And then, of course, this point would be away from my orientation has changed. So when I look at this type of transformation here, well, S and S prime, there's my indications that this would be this is my pre-image. And then when I see S prime, that would be considered my new image. And when I say S prime, this would be Q prime, this would be R prime, and that's how that's read, or how you should read that and understand the translations there. So showing the first movement, and we can see that R is right here and Q is right here. Well, none of the sides flipped far away from each other as in a reflection. You know, I can't draw a line in here to say it crossed over a line. Slide-wise, if I were to look at the translation, they don't seem to go all the same distance and angle. So we're looking at a rotation, and so we probably rotated around some point, and we did this: rotate, rotate, rotate. So the whole image has rotated around a center of rotation. So that is a rotation. Looking here at this next transformation, what transformation maps A to A prime, B to B prime, and C to C prime? Well, there you have it. That they all look like they're traveling the same distance in the same direction. So that would be a translation, those characteristics. Now, continuing on with transformations, we have another type of transformation, and that is a non-rigid transformation. Now, remember when we had rigid transformations, that isometry, everything remained the same, and the pre-image and the new image, or the starting point and the finishing point, the image was congruent. Everything stayed the same. Well, when we come to a non-rigid transformation, it is a transformation that does not preserve the size, length, shape, side, or angle measures of a figure. And the pre-image and the image, therefore, if it isn't preserved, they are not going to be congruent. And if we look, this first example right here, in a dilation, things, everything, it says the pre-image is proportionally enlarged or reduced. So if this was my pre-image, and I go to a image, if you notice, this side corresponds to this side, and it has doubled in size. This side corresponds to this side, and it has doubled. This side corresponds to this side, it has doubled. This side corresponds to this side, and it has doubled. So what happens if we go from this to this, we have enlarged the object. If we were to go from the bigger object to the smaller object, we would have reduced the size of that object. So we either enlarged by doubling, or we reduced by cutting everything in half. It just depends on which way you're looking at it. And again, a dilation, everything remains the same. So proportionally, so as this piece increased, if this piece, as it became one to the other, everything enlarged the same. Let's see here. Now, for a stretch, on the other hand, a stretch, that's what they call this, a stretch. There is proportional enlargement or reduction, but only in one dimension. So if we can see here, we have, let's call this a little pennant flag, right? We have a little looking like pennant flag, maybe from a university, and this is 2, this is 3, and 3. Well, if you notice, this new image, this length right here remained the same, corresponds over here, remained the same, but the other two lengths stretched out and doubled. So it's almost like I pulled this pennant right here, and I just pulled it out until I had doubled its length. So there is a corresponding stretch. And then the same goes here, that this side and this side are congruent. Well, if you notice on my new image, this side and this side are still the same. So it's almost like they stretched, this parallelogram out, and they stretched this side to double it and pulled it out this way. So that is the difference between a dilation and a stretch. A dilation, all sides transform proportionally, and then on a stretch, one dimension remains the same. So transformation notation. We have touched on this a little bit as I've been giving some examples, but prime notation is used to indicate that a figure has undergone a transformation. So prime notation, this would be an example of prime notation. So if this is it, I will tell you that this is a translated. It says triangle ABC has been translated. So A corresponds to A prime, B corresponds to B prime, and C corresponds to C prime. So triangle ABC corresponds to triangle A prime, B prime, C prime. And that is, this would be my pre-image. This would be my image. Point point A corresponds to, A prime, and then segment CB corresponds to C prime, B prime, and then angle ABC, which is this angle right here, corresponds to angle A prime, B prime, C prime. So there you have it. We're talking about that proper notation. Then when we discuss mapping, and I've used this term, but more definitively, a transformation maps to a figure onto a transformation maps a figure onto its image. So an arrow is used to indicate the mapping. So this is right here. So what we would have is C maps to C prime. C maps to C prime, and that's how you would say that. And then you would say that triangle ABC maps to triangle A prime, B prime, and C prime. That is how we term or say the proper mapping and how we would indicate it on a piece of paper if having to write the answer. So looking at our examples, you may recognize this first example we're going into. So example number 4, we have what type of transformation is this? So I hope that you can say, well, my orientation changes. You know, the orientation of my sides changes, so it's not a translation. I don't have any opposite forming sides, so it's not a reflection. So therefore, we're probably looking at some form of, again, rotation. And we could say that rotates like this, rotates like this, rotates like this. So everything rotates around some imaginary point that must be out here, because the distance from S to S prime is going to be the same. The distance from R to R prime is going to be the same because it's just rotating around the point. It's not changing shape or sides. Let's see here. We're looking at some more transformations here in number 5. Which transformation shows a reflection? Well, a reflection. I tell you, I'm just going to go ahead and say it looks like if I were to put a line of reflection between those two, it's not perfect. I could say that that is probably the closest image to a reflection, because the distance from D to my line of reflection, and we'll just call it M, is going to be the same as the distance from that same point to D prime. The same thing goes here. From E to the line, E prime to the line, that distance is going to be the same. And then from F to the line and F prime to the line will be the same. So it seems like we have a reflection, a mirror image there. If I look at my other examples, I can see that this example over here, D to D prime, E to E prime, and F to F prime, this turns out to be a translation because everything is going in the same direction, the same length. So that's a translation. And this one over here, let's see. It looks like I did some kind of rotation. Because I've gone from E to E prime. And if we look, probably that distance from D to D prime could be the same. So that could be a rotation of some sort. The rotation point might be more like right there. But my orientation has changed, and we can see that everything appears to be traveling in a certain angle. Okay, so that was more than we asked for on example number 5, but I tried to show why we came up with a reflection. Now, which type of transformation maps trapezoid PQRS to P prime, Q prime, R prime, S prime? All right, well, let's look. What kind of transformation? I can see here, just looking at one length, PS. So PS corresponds to P prime S prime corresponds to PS. So I should be able to look at this and say, this is my image. Sorry. This is my pre-image, because that's where I started. And then this is my new image because it has my prime indicators. And I can just pick, let's see here. PQ corresponds to P prime Q prime. So I went from PQ, this was 2, and then now it's only 1. So it looks like I decreased by 1/2, right? 1/2. Let's see, QR, 4 down to 2, so it looks like that was by 1/2. And sure enough, RS, R prime, S prime, 1/2, and then finally PS to P prime, S prime, right, is 1/2. So it looks like everything changed by the same factor, so that would be a dilation. And then here, looking at my word problem, all side lengths of JKL equal 2. 2, JKL. That's a really ugly triangle, but you get the point. A transformation maps to this J prime, K prime, L prime, and the lengths of side JK is 5 units. J prime, K prime is 5 units. Is this rigid? Well, JK used to be 2, and they're saying that now JK, J prime, K prime is 5. Well, that's not rigid. No, that's not rigid because the length didn't stay the same, so it's not rigid. We don't really need to do anything more than that to say, heck, it used to be 2, now it's 5. It changed. It's no longer congruent, so it's not rigid. And that is a brief introduction to all of our transformations that we are going to be spending the next week and a half talking about. And again, we will have a focus day on each one of the transformations, but this is just a broad overview, being able to recognize what is going on.